Okay, so first, a brief review of the things we learned last time. Necessary condition and sufficient condition. For example, if P implies Q, then P is necessary condition for Q. Okay. Now, sometimes we say a condition is necessary and sufficient. We use P and Q, we see they're equivalent, necessary and sufficient. We have many applications of this. Several of our theorems can be reformulated in this way, using the necessary and sufficient condition. Very interesting one is the intercept theorem. The intercept theorem, if EF parallel to BC, find the ratio. This is a sufficient condition. We also that this is also necessary, so they are actually equivalent. Then we introduced the four trigonometric functions. Aaron, give me an example of the trigonometric functions. What are the functions? Give me one example.
Uh, let's see now. Sin, what's that thing called? Omega.
Theta?
Oh, sorry, I meant
Okay.
theta.
Okay. Kira, another one.
Cosine?
Cosine theta. Okay.
Wait, question. Isn't
Yes.
it supposed to be a triangle? Why did I switch to a O?
Which is O? You mean this?
Yes,
Okay. So this is the Greek letter called theta. Okay. Maybe I should introduce
but
this.
I said the date. Oh, I thought it said delta.
Okay. Delta will be this.
Ah, but isn't delta also a triangle?
Uh, so that's the capital letter, capital theta, and the capital delta.
I see.
Uh, okay. Isabel, third one. Okay, maybe not here yet. Let me check with her. Okay, she's here. Okay, Isabel, another trigonometric function besides sine and cosine.
Tangent.
Tangent. Okay, Peter, turn the camera, Peter. Okay, so he will do it later. Okay, so the last one will be cotangent. Okay, so initially, these functions are defined, for the first two, they're defined, maybe let's start with all of them. Okay, so because in this case, we can use the right triangle to define these functions. Okay, so we can see this is definition. We have a right triangle. Okay, so the ratio BC, the side facing theta, over AB, hypotenuse side, we define this as sine theta. The side adjacent to it, AC, over AB, defined as cosine. The ratio simplify BC over AC. This one is reciprocal. AC over BC is the reciprocal. Okay, if someone else comes in, he give you a different right triangle. E and F. Okay, use this new triangle. He has a different definition of sine theta. Let's see. Using the new triangle will be EF over AF is E. Okay, so now two right triangles, two ways to compute sine theta. Now think about this. How do you convince others these two give us the same result? If the triangle changes, do we get a different result or it must be the same? Why? How to argue this? Aaron,
B is congruent to BC. I mean, EF is congruent to BC. Sorry, pronounced that wrong.
What do you mean congruent? EF congruent?
I mean like they're like same direction.
Okay, that's a parallel.
Yes, parallel.
Okay. So here a key observation is that EF is parallel to BC.
I meant congruent as parallel.
Okay, yes. Okay. Kira, why Are the two lines parallel?
I sort of forget how to do this.
Uh-huh. Okay. Isabel, what about you? Any guesses?
I think so.
Why?
Because it's like corresponding angles and like they're like right triangles.
Okay, so the two angles, they are all 90 degrees. In particular, they are the same. Okay, so yes. Therefore, even though the triangles are different, the ratio is the same. Okay, so these functions are well defined. Okay, now let's consider the two angles. Again, a right triangle. A, B, C. These two angles, let's call it alpha and beta. Again, Greek letters because we use angles them for angles very often. So alpha and beta. Okay. Uh, Fred, are you here, Fred? Can you hear us? Okay. Aaron, what are they called? Alpha and beta. Any connection between them?
They're both on AB, the line.
Uh-huh. Okay. So what's the summation of the two angles?
Uh, let's see now. They're both angles.
Okay. What's alpha plus beta?
Oh, okay. A squared plus B squared equals C squared.
No, that's for the side, not for the angles.
Oh, I swear I forgot.
Kira,
All three the all three corners of a triangle added to 180, so it's a plus b equals 180 minus 90, so that's 90.
okay. So this is 90 because the interior angles theorem, the summation of the three give us 180. This one is 90, so the remaining two also 90. Two angles, that the summation is 90. What are they called? Isabel, alpha and beta, they are
Complacent. I mean,
complementary.
like supplementary, yeah, sorry.
Supplementary is the next one, so this complementary. Okay. Supplementary, two angles. Let's use uh, gamma and theta. This time we call it supplementary. Okay, so the difference and the similarity between the two. Complementary addition 90 degrees. Supplementary addition 180. Okay, the, let's see. For this angle alpha, we compute sine alpha, cosine alpha. For this angle beta, we computed sine alpha, beta, cosine beta. Are they connected? How are they connected? Sine alpha, cosine alpha. Any connection between the pairs? Fred, what do you think, Fred? Alpha and beta. Anyone else? Isabel, what do you think?
Not sure.
Okay, so if we check the definition, okay, let's see. Kira, what's the definition of sine alpha?
The side that's facing it, like opposite.
The side facing it will be BC over AB. Aaron, what's cosine alpha?
The side on the angle.
So
That's not.
AC over AB.
Mm-hmm.
Isabel, sine beta.
I think it's
Sine. Opposite side
AC over BC.
AC over the hypotenuse side.
Oh, AC over AB.
AC over AB. Fred, cosine beta.
Cosine beta equal
There will be a ratio. There will be the side adjacent to it over the hypotenuse side. This will be BC over AB. Now let's check. Do you see repeated numbers? Aaron, are there repeated ratios?
They're the same ratio, but like flipped.
Okay. So sine alpha becomes cosine beta. Cosine alpha sine beta. So this is the
That's what I said.
property about the trigonometric functions. If two angles are complementary, their sine and cosine is flipped. Okay, that's our theorem. Okay, theorem. Sine 90 degree minus alpha. We just observed. So here, because beta is used this expression in our theorem. If two angles are complementary, the sine and the cosine get flipped. Now we know sine and cosine. I will give you a few minutes to think about the rules for tangent and the cotangent. Okay, let's figure out the formulas for these two functions for complementary angles. You can enter the answer in the chat if you finish. Okay. Any thought? Kira, any thought on this?
Not really.
Okay. So what's the first step? What's the definition of tangent?
Well,
Like sine of
Sine
something
over
over
cosine.
cosine.
Okay. Is sine. Okay, let's do it in another line and copy the result later. Of tangent. By definition, it's the quotient of sine and cosine. Okay. Okay, now we are going to apply the two formulas we already obtained. Aaron, what do you say about the numerator? Can you simplify the numerator? Sine,
okay, cos alpha over sin alpha.
which is cosine over sine.
Right?
What's this function?
Um, cotan.
Right, cotangent. So this will be cotangent. In the same way, you can verify this is tangent. Properties about the sine function, cosine function, tangent, and cotangent for complementary angles. Next, supplementary angles. Used it. Okay. For supplementary angles, we have different formulas. Sine stay sine, but cosine go to the opposite. Okay, with this, let's find tangent and cotangent. What are the formulas? Okay, enter your answer in the chat when you're done.
That's just
Yeah.
that first one is simply just tan theta.
Okay, so our first guess, our first result.
Tan for tan.
Aaron,
Right.
is that what you said?
I said negative cotan.
Okay, nice.
I think.
That's correct.
Yeah.
Okay. Kira, are you getting the same result or different?
Which line of the triangle is the tan exactly?
Okay, so if we go to the definition, tangent will be the opposite BC over the neighboring. Cotangent is the flip, neighboring over the opposite. So for this question, what we need is what you had proven in the same method because tangent is quotient of the two, sine over cosine. When we apply the two formulas,
So it'll be
get
sine
the
over negative cosine.
exactly, yes. Yes. Isabel, the last one. Why?
Uh,
So how do we define the cotangent? If we go to the previous page, you can see cotangent, cosine over sine.
mhm.
So this one will be cosine over sine. Then we apply the two formulas.
Then it will be like a negative.
Yes, there'll be negative cosine over sine, negative sine.
Okay.
Okay, so the formulas. Okay, so with these functions, we have two important laws. One about sine, one about cosine. A, B, C. Okay, so here, when we define these functions, we started with a right triangle. But after that, the applications goes beyond this. We can apply it to any triangle. So here, if we want sine beta, we cannot apply the formula mechanically. We cannot say it's the quotient of the two. That doesn't work. That formula only applies if we have a right triangle. So here, sine B is defined. Okay, let's go with all three of them. Angle A, angle B. Again, we label the opposite side lowercase letters A, B, C. Then the sine law tell us over A, over B, over C, all three ratios are the same. Okay, let's recall how we proved that. Let's start with one of them. Let's recall how we verified this one. Why are these two equal? To prove this,
Oh yeah, that's a
we
wait.
yes,
That's the law of sines, right?
so, Aaron, what's that again?
Uh, you said that in the notes last week. Something about that's the law of sines, right?
Uh-huh. So this is law of sine.
Ah,
Okay. So why is this? We can draw perpendicular line and label the foot. Okay. Now who can tell me the area of the triangle ABC?
it's let me think. If I got this correct, it's AB times the BC over half.
almost if we have a right triangle.
Aha.
So here's a general triangle, not necessarily right angle.
Hold on.
Okay, Isabel.
Oh wait, sorry, I was muted. I think you use BC times AD over 2.
Okay, so we can use the formula 1/2 of the base times the height. 1/2 BCAD. Okay, now we have two ways to understand this AD. First way, using this right triangle. Let's start with there. Okay. Use the left side right triangle because it's perpendicular. Perpendicular sine B is the opposite over hypotenuse. So the area is AD because AB BC sine B. So it gives us another way to find the area without using the height. If we know one side, second side, and the sine of the angle between them, then this formula gives us the area. Very useful formula. Okay, now let's do the same thing using the other half. Okay, I will give a minute, 2 minutes to think about this. If we use this right triangle, how to represent AD? Fred, any thoughts on this one? Kira, previous one, sine B. New one, about the AD. Uh-huh.
I think it might be like this, but I'm giving a theoretical guess, but AC times sine angle C
Why?
because
That's
the two sides are what's it called?
okay. So
I
this will
forgot what
be
it's called.
A sine angle C because this is a right triangle.
Right. They're
Yes.
parallel.
Okay. So we can do the same thing. We get another formula for the area. AC, BC. Now if we combine these two equations, two identities, they both equals AD. What can we say about the two? Isabel, what can you say about the two?
I think they're the same.
It must be the same because they both equal AD. 3, 1, different color. Now we can write this as a quotient. So sine angle B over AC. Sine angle C over AB. And this is part of the law of sines. That's how we prove this law of sine. We can draw perpendicular lines, find the two equivalent expressions for the height. One use angle B, one use angle C. Then they must be the same. You can prove this in a similar way. You draw perpendicular lines. Okay, so I will skip that part. And so this is law of sine. Then we have law of cosine. Okay, make a triangle. A, B, C. Law of cosine. If we label this lowercase a, b, c, cosine. There are different ways to formulate this. One is if we know the three sides, we can find the cosine of the three angles. So cosine angle C is the quotient, numerator two neighbor sides, a square plus b square. Subtract the square of the opposite side divided by 2ab. Let's consider a particular case. A particular case when a is 3. Example. Let's find cosine C. Okay, I will give it 15 minutes to finish the calculation. Enter your answer in the chat when you are done.
The chat is locked. It says that
What is it locked?
I can't answer right now for some reason.
Oh, okay. I see. Let me check. Let's check again. Aaron. Okay, okay. I hear an answer. Aaron, think about the answer. It's correct. What does it mean?
What?
Cosine is zero.
Yes.
What does that mean?
Well, okay, so if 3 equals 8, then that's 9, and if 4 equals B, that's 16, and C, that's 5, so that's basically 25 minus 25 over 24, right? Mm-hmm.
Okay, so whenever the cosine is zero, it means this angle is a right angle. It is a right triangle. Okay, so the observation is actually it is a right triangle. Okay, so law of cosines can tell us whether this data give us a general triangle or a right triangle. If we get zero, it must be a right triangle. Okay, any question about this one? We will have 5 minutes break and be back at 8:19.
Okay.
Okay, 5 minutes break. Next, we will start a new chapter, chapter 5, about circles. The first time we encountered circles in this class is the Euclid 5 postulate. Okay, now it's a good time to recall what they are. What are the 5 postulates of Euclid?
I forgot what the entire word was, but it was something about a straight line reaching a given point.
Okay, the first one,
Yep.
any 2 points, we can draw a line through them. Okay, my line is off. Okay, let's move the points. Maybe that's easier. Any 2 points, there's a line. Second, postulate. But any segment can be extended in both ways. Oh, let's see. Okay. What's the third one? Okay, Kira.
Is the third one the one about circles, or is that the fourth one?
Okay,
Well,
third
one of
one
them is
about-
like a circle can be drawn with any given radius.
Okay, so any point, any radius, we can draw a circle. Let me try to draw one. Hopefully it is a good one. Okay, not bad. What's the fourth postulate? Okay, yes, Kira.
All right angles are equal.
All right angles are equal. Whether you go this way or you go that way, or you, oh, that's not the right angle. Okay, they are all the same. Last one. Last one is about the transversal of two lines. We check the summation of two interior angles on the same side. 1 and 2. If the summation is less than 180, intersect on that side. It means if we extend the line, they will intersect on this side. And this is also called the parallel postulate. It gives us condition when two lines are parallel. The parallel if the summation is 180. Okay. So now we will learn more about the circles. So circles has a point, we call it the center, and radius. O, the capital O, a point. A set of points. With the distance. So we call this a circle. And O is the center of the circle. R is called radius. Okay, very nice. Let's draw a circle. Next, we consider a point outside the circle. Let's compare the distance. Which is bigger for points outside the circle? Kira, if a point is out in exterior, what can you say about the distance? Bigger, equal, smaller?
It's bigger than the radius.
It's bigger than the radius. Okay, we can write this as bigger. If we pick a point in the interior, see, what can we say about the distance? Aaron, we want to compare OM and R. In the interior, the distance must be smaller. So this gives us the characterizations of points.
Excuse me.
Yes,
Isn't it kill exterior?
yes.
It looks more like an N to me.
What's that?
You wrote anterior instead of exterior. Kind of looks like it.
Okay. Let me correct this. I rewrite it. EX. Little bit better. Okay.
Yeah.
Okay. So this is interior. So a circle divides the plane into three parts. Exterior, where the distance is bigger than R. Interior, where the distance is less than R. And the circle itself, the distance equals R. Next, consider a segment on the circle. Okay, let's move the point a little bit. We call this point A and B. A segment connecting 2 points on the circle. We call it a chord. Okay. As the point changes, the chord changes. May go longer, may get shorter. Okay. What's the longest chord?
Diameter.
Okay, the longest chord goes through the center. It's called the diameter. Okay. And the diameter satisfies is twice of the radius. All right, let's draw another circle. This time we have a point. Let's draw chord. Okay. We will call P the vertex. PA and PB, two chords. Okay. We call this angle APB. We call it an inscribed angle. Another one is we mark the center O and connect angle AOB. Call this. Okay. Okay. Two chords with a common vertex. The angle at the vertex we call it an inscribed angle. And the angle at the center, a central angle. Okay. The first question, if we fix A and B and move P around the circle, how does this angle change? Okay, you can draw a circle, try to move the point around. Let me draw another one. I can move P to another position. Put the tilt over there. These two angles, is one bigger, one smaller, or not? When P moves around, how does this angle change? Or does it change at all? Isabel, think about the question. If we move the points, how does the angle change? Aaron, what do you see?
Well, PA is definitely not equal to PB now.
What's that? I didn't catch it.
I'm saying that PA is definitely shorter than PB now.
Okay, so it's possible. If we move the point over there, PA will be shorter. If we move points this way, PA will be longer. The sides may be longer, may be shorter. But our focus is on this angle.
Oh, I don't see any change.
Okay, that's a very good observation. The angle does not change at all. Is our next theorem. Angle AOB is twice angle AP. Okay, see, when P slides on the circle, this angle stay the same. And this is always half of the central angle. Angle APB half angle AOB. Very interesting observation. No matter how this point changes, it may go to left, it may go to right, the angle stay the same. Okay, so why is this? Okay, I'm going to make a copy of the graph in the next page. Draw a circle with 2 points. Kind of arbitrary. Another point. Connect them. Connect them. we want to prove this angle is twice of this angle. So here I will give you one proof. In the homework, I will ask you to give another proof, two different proofs. So for this proof, I will connect the 2 points, P and O, and extend it. Draw the diameter. Okay. All right, let's consider the triangle. A, O, P. Okay, what can you say about this triangle? A, O, P. Any special features about this? A, O, P.
It's half of uh uh it's half of ABP.
Not necessarily, because
I mean, like,
this is thinner, this is thicker,
oh,
right?
I thought you were looking at it from 3D, but yeah.
Okay, it's 2D, just the plane. Okay. So Aaron, what's this length? OA. Unmute. Aaron.
I'm not quite sure.
O is the center. A is a point on the circle. What's the distance?
R.
R is the radius. What about OP?
That's also R,
Also R.
I think.
Okay, that's correct. It's the radius. Now, this triangle, the two sides, both are. What do we call about triangle with this property?
Sorry.
Okay, there's a special term for this
Diameter.
about triangle. A triangle with two equal sides.
Actually, no, it's not diameter. It's not, I kind of forgot
Called
what it is.
isosceles.
Oh,
Mhm. In particular, the two angles corresponding to the two sides. OPA, OAP. Okay, so we proved one theorem about this. Equal side, equal angle. Equal sides, equal angles. Okay. Next is let's recall the exterior angle theorem. What does it say? the triangle AOP, this angle AOD is an exterior angle of the triangle. Okay, try to recall what the exterior angle theorem tells us. Isabel, the exterior angle theorem. Do you still remember this?
I think. Oh wait, I don't think I do, sorry.
Okay, This is an exterior angle. The exterior angle tell us this equals the summation of the two remaining angles.
Wait, you're saying angle O equals angle A plus angle P.
Yes.
Oh, right.
So this is the exterior angle theorem. But we already showed these two angles are the same. So it will be twice of this one. Go AOAP, OPA. Okay, because the two angles are the same. Okay, so this angle is twice of this angle. It's half of what we want. Next, we will show that this angle is twice of this angle. Think about why. This is step one. Step two. Consider the triangle. BOP. Again, I want to say this is an isosceles triangle. What's the argument for this? Why?
OP equals OB.
Okay, so OP. Isosceles. What does this tell us about the angles?
Um,
Mm-hmm.
OPB equals OBP.
OPB. My O looks like a B, so let me rewrite this. Angle OPB, angle OBP. Nice. Again, we will apply the exterior angle theorem. This time, let's move to angle BOD. Okay, what does the exterior angle theorem tells us?
BOD equals OP
Mm-hmm.
plus OBP, which therefore is to OPB.
OPB angle OBP. Again, because the two angles are the same, will be twice angle OPB. All right, we have both. Now let's add them. What's the summation of angle AOD, angle BOD?
AOB.
AOB. Okay, so angle first step should that AOD is twice angle OPA. BOD second step is twice of angle OPB. So twice angle OPA, angle OPB. Okay, what's the summation of these two angles? OPA, OPB. OPA, OPB. This will be APB.
2 APB.
APB, twice of APB. So in this way, we show that this angle is always half of this angle. The inscribed angle is half of the central angle because this is half of this one, this is the half of this one. Summation is half of the central angle. When P moves on the circle, this angle stays the same. In particular, when P moves to another point on the circle, the two angles are the same. Very useful theorem, and we will use this many times in the future. So you should remember this and how we prove it. In our homework, I will ask you to give a different proof, similar but slightly different. Okay, questions about this? Let me stop.